Welcome back. We are going to continue the 2017 AP Calculus AB exam, Part 1, Section A. This video will cover questions 11 through 20, and as terrifying as it may sound, but it's really not that bad, no calculator is allowed for this part of the examination. Wonderful. Wunderbar. Let's begin with question 11. Okay, if x squared plus xy minus 3y equals 3, then at the point 2, 1, dy dx equals. We basically need to find the derivative of our equation at the point where x is 2 and y is 1. Now, I'm going to take the derivative of this implicitly. I don't have an equation that's just y equals. Could I maybe manipulate it and get the y alone? Sure, but you really need to know how to take implicit differentiation. All that means is you take the derivative of every x like you normally would, and you take the derivative of every y just like it's an x, except when you take the derivative of the y, you write dy dx right next to it. Let's begin. The derivative of x squared, well, that's just 2x, plus these two variables are being multiplied, so it's the product rule. It is the first term, x, times the derivative of the second term, okay? The derivative of y is 1, but anytime we take the derivative of y, we need to put dy dx next to it. Now, I could have written my 1, dy dx, but you don't really have to write the 1. So, we just took the first times the derivative of the second, plus the second, which is my y, times the derivative of the first. The derivative of x is 1. I don't have to write that 1. It's going to be 1y, so I'm going to leave it just like that, 1y. All right. Minus the derivative of 3y is just 3. But anytime I take the derivative of y, I need to write dy dx next to it. Okay? Equals. I got to take the derivative of this side as well. 3 is a constant. Derivative of a constant, 0. Now, what I want to do, the whole goal here, is I want to have any term with dy dx on one side. Okay, so I'm going to keep this and this. And I'm going to eventually factor out that dy dx, so I only have one of them instead of two. I should put the parentheses here. Okay, so I'm going to subtract 2x from both sides, and I'm going to subtract y from both sides. Boom, bang, done. So I've got x dy dx minus 3, because I've got these left, dy dx equals negative 2x minus y. All right? Now, I said I was going to factor these out. Okay, I'm going to factor these out. So I've got dy dx. And what's left after I factor them out? Well, I have my x and my minus 3. Negative 2x minus y. Last step is I'm going to divide both sides by x minus 3. Now I've got my dy dx alone. And what I do to one side, I need to do to the other. So minus 2x minus y all over x minus 3. Now, I need the derivative, but I need a number. Okay? And what that number is depends on where or what point I have. My x is 2. Wherever there's an x, I'm going to plug in a 2. My y is 1. So wherever there's a y, boop, right there, I'm going to plug in a 1. So let's go ahead and do that. Okay? This is going to have a 2 in it plugged in here, and a 2 plugged in here. I'm going to have a 1 plugged in here. 2 times negative 2 will be negative 4 minus 1, which is negative 5. And 2 minus 3 is negative 1. My goodness, is the answer 5? It's a lot of work for a multiple choice problem. But if I wasn't explaining it and I was just doing it and going quicker, it wouldn't take so long. But our answer should be 5. Number 12. Don't overcomplicate it. Do not overcomplicate it. It's simple. The number of gallons of water in a storage tank at time t in minutes is modeled by W of t, which equals 25 minus t squared, for t values between and including 0 and 5. Okay? At what rate in gallons per minute is the amount of water in the tank changing at time t equals 3? Changing, okay? Let me go color here. Changing. It's a rate in gallons per minute. If I need to find a rate, okay, of something that is just gallons, and I want like gallons per minute, I got to take the derivative of it. W prime of t. Okay, well, the derivative of 25 is 0, minus the derivative of t squared is 2t. So really, it's just negative 2t. That's the derivative. At what point? At time is 3. Negative 2 times my time of 3. Negative 6. That's gallons per minute. I don't care. I'm just circling the negative 6. Choice D. Very simple. Don't complicate things if they are not complicated. Number 13. Shown above is a slope field for which of the following differential equations? Okay, and we got this mammoth of a slope field right here. Goodness. Sometimes these are hard to kind of teach. The best way that I can suggest is kind of like picking an area, checking out the slope, and see if it's possible. So what do I mean? Let me start out by saying that some of these options, option A, and option C, you have an X here, okay? B and D you do not. So let's take a look at that X first. We're going to try and get rid of half of these. Either we're going to cross out A and C, or we're going to cross out B and D. So we're going to start to narrow this down. I'm going to look at whenever X is 0, okay? X is 0 right here. So anywhere on the y-axis would have, wow, that's a really bad line. Anywhere on the y-axis would have an x value of 0, okay? So I'm going to pick just any random point, and I'm going to pick the one that's obvious. And by obvious to me is they actually have a mark here where x is 2 and, where x is 0 and y is 2. So I'm going to pick this point. So, this point right there, x is 0, y is 2, okay? That is a positive slope, okay? If you'll notice, anytime x is 0 on this line here, they're all positive slopes. All right, so let me take a look down here. Here's the issue with when x is 0. Okay, if I put a 0 here, 0 times anything would still be 0 on the top. If I made this x 0, 0 times anything would still make a 0 on the top. They would have a horizontal line, my slopes. Are any of the lines where x is 0, are these horizontal slopes? No. This is close. It's not quite, though. So they're not horizontal slopes. So my x can't be 0. Okay, by process of elimination, it cannot be this one or this one. Okay, so I'm just going to get those out of sight, out of mind. Okay, man, like I am horrible. I am going right into this one. I need to see this. All right. So now that leaves us 2 more to evaluate. The only difference between choice B and choice D is you have a y and a y squared. Okay? Everything else is the same. You still have 4 minus y over y, 4 minus y over y. And if you know anything about numbers, you'll realize that a major difference is here, when I just have y, I can have positive or negative values. Okay? When I have y squared, it doesn't matter if it's a positive y value or a negative y value. When I square it, it will always be positive. Okay? So I'm going to look at that right now. Let's pick a negative value, okay? Because that's going to, if I picked a positive value, if I picked 4, I'm going to end up positive here, y, and this will be positive. But let's pick a negative value, because a negative value will indeed make choice B have a negative number here. But if I have a negative value here for choice D, I will square it and it will become positive. So let's pick a negative y value. I don't know. The x value doesn't matter. Let's pick somewhere, I don't know, -1 for my y. Okay? This slope is a positive slope. It goes up like this. At y is approximately -1. So let's plug a -1 into here. Okay? If I have -1 for y times 4 minus a -1 all over 4, that would give me -1. This would turn to 5 over 4. That would be -5/4. That's a positive slope. That goes like this. It can't be this one either. By process of elimination, it's D. And just for poops and giggles, yeah, I almost said something else. Let's try throwing a -1 in for y here. If I have -1, I'm squaring it this time, right there, times 4 minus a -1 all over 4. That's a +1 times 5 over 4. That's a +5/4. That is absolutely 110% positive slope. D. You're really going to have to kind of just look around and get a feel and try some things through trial and error and start with things that are easiest, when x might be 0, y might be 0, and build from there. Number 14. A little bit of a challenging problem, but follow me. The weight of a population of yeast is given by a differentiable function y, where y of t is measured in grams and t is measured in days. The weight of the yeast population increases according to the equation dy dt equals ky, where k is a constant. At time t equals 0, the weight of the yeast population is 120 grams. That's probably going to help at some point. And is increasing at the rate of 24 grams per day. Which of the following is an expression for y of t? Oh boy. All right, the first thing you need to realize is when I have this right here, and they want an equation for y, I'm going to have to use separable differentiable equations. Okay, we're going to have two integrals going. Okay, all right, what do I mean? Well, I got dy over dt equals ky. All right, I want my y and dy on one side, and I want my k and dt on the other. And you might be saying to yourself, well, k and t aren't the same variables. K is not a variable. K is a constant. Think of it as like the number 5. Okay? So I'm going to multiply this side by 1 over y. This cancels with this. I multiply it by 1 over y. I'm going to multiply the left side by dt. So this will cancel with this. And I multiply the right side by dt. So let me clean this up. And when everything is all said and done, I have 1y dy equals k dt. At this point, I have two differential equations that I can integrate. Okay? I'm going to integrate this side, and I'm going to integrate this side. Now, the integration of 1 over y is the L n of y. And I still have to have my plus c, because there are no bounds, so I always need to have my plus c, my constant, equals. Remember when I said think of k as 5? If k was 5 and I was integrating it, it would go to 5t. How do I know it's t? I'm using t here. Okay, but we don't have 5. We have k. So instead of 5, I'm going to call that k t plus c. All right? Believe it or not, those c's are different values. I mean, maybe they're the same, but I could have the c on the left be 5, the c on the right be 7. I could have the c on the left be -2. I can have the c on the right be 13 million. So I always do this. I say it's C1 and C2. All right? Now, I want to get my y alone. All right? I want to get that y alone. So the first thing I'm going to do is I'm going to get rid of the c on the left-hand side. Okay? So I subtract C1, subtract C1. And I've got the ln of y equals kt plus c. Right? If I have one constant and I combine it with another constant, I will end up with a constant. All right? Now, I still need to get that y alone. So I'm going to raise both sides. Okay, I'm going to apply a base of e to both sides. E and L uncancel. Badoosh. We'll go up here for the sake of room, and I just have my y equals. This is all one exponent. All right? The rule of thumb is, what do I do in order to add exponents? I need to multiply things with similar bases. So if I had x squared times x to the 5, isn't that x to the 2 plus 5, or x7? It is. So what I'm going to do here is I'm going to start with this and break it apart into multiplication. So y equals e to the kt times e to the c. Do you understand what I did here? So now if I were to multiply these two together, I would have my 1e with my exponents added. Here's something else. K is a constant. Guess what? E is a constant as well. E is the number 2.718, etc., etc. It goes on forever like pi. Euclid's number. Now, any constant raised to a constant is still going to be just a constant. So I will rewrite the right side as a constant times e to the kt equals y. Now, I don't know k yet, that's fine, but I need to find c. I don't know how I'm going to find. Actually, I know exactly how I'm going to find c. I mean, looking at it here, I'm a little bit like, you know, okay, I got to a good part, did a lot of good math. These things are going to come in handy a couple of times. At time 0, the population is 120 grams. Okay? At time 0, population is 120 grams. So now I've got c e to the 0 equals 120. E to the 0 is 1. Goes bye-bye. My c is 120. That was actually very simple. And look at us. We were a little bit nervous. Now, let's replace my c with 120. All right? We're almost done. We have y equals, I keep on making it look like a question mark, 120 in for c, e to the kt. If I look at my answers, it can be either A or B. It's not this, okay? So is k going to be 24, or is k going to be 1/5? How do I figure out what k is? I had said a few moments ago that when time is 0, population was 120. That's going to come in handy a couple of times. Look what follows that. Time is 0. Okay. 120 is the population at a rate of 24 grams per day. You ready? Do I have a rate anywhere? This is the rate right here. dy dt represents the rate, which is 24. So I'm going to say 24, which is my dy dt, equals k times y. What is y? Y is population. Okay. There you go. There you go. So let's divide both sides by 120. And yeah, that is 1 over 5. That equals my k. That's my constant k. So that 1/5, and this is a lot of work. This is a tough problem. It's a complicated problem. 1/5 k, that's going to go in for my k value right here. So when everything's all said and done, I have y equals 120 e to the k t. I can say 1/5 t, or I can say t over 5, or I can simply say it's choice B. That problem took some work. That was a pretty tough problem. Number 15, the graphs of the functions f and g are shown in the figures above. Which of the following statements is false? Okay, that means 3 of these are true. Just don't look at the first true one and circle it. Don't get in that habit. We want the one that's false. All right, let's just go down the line here, okay? A says the limit of f of x as x approaches 1 is 0. Okay, well, as x approaches 1, this way, yeah, the limit is indeed 0. Okay, that's true. Okay? The limit as x approaches 2 of g of x does not exist. Well, here's the line x is 2. As I approach it from this side, it has a y value of 1. As I approach it from this side, it has a y value of -1. They are not the same. So it's true. It does not exist. All right, let's look at choice C. Bam. C says, okay, the limit of f of x, g of x plus 1 does not exist. Ew. All right, well, let's use some of our limit rules here. If I'm multiplying two functions, I can take the limit of both of them individually and then multiply it. Kind of like distributing, not really, but kind of. The limit as x approaches 1 of f of x, all right? And then the limit as x approaches 1 of g of x. Ooh, of x plus 1. Look at me go. That's an important thing. Bam. Plus 1. All right. Well, the limit as x approaches 1 of f of x we just did is 0. We're going to multiply these together. And, all right, as x approaches 1, now this, and we just went over this in my Algebra 2 class, this represents a movement. That's 1 to the left. If I'm adding inside the parentheses of a function, okay, that represents horizontal movement. If I'm adding 1, that means I'm moving to the left 1. Okay, so, if I'm moving to the left 1 here, here's 1, I'm moving to the left 1. It doesn't matter, it's the same thing. I was here as x approaches 1, but I'm going to move left 1, so let's take the limit here, and that's still a y value of 1. 0 times 1 is 0. If it's 0, it does exist. 0 is a value. That is not undefined. It's an actual number, kids. Guess what? Which means it does exist. That's wrong. So this is false. All right, look at us go. Got to remember those rules from Algebra 2. That's terrible, but it's so good. Number 16. I like these types of problems. Let f be the function defined by f of x equals negative 3 plus 6x squared minus 2x cubed. What is the largest open interval on which the graph of f is both concave up and increasing? If it's concave up, that means the second derivative is positive. And if it's increasing, that means it has a positive slope. That means the first derivative is also positive. So let's start taking the derivative and figuring our stuff out. The derivative of f of x is 0. Okay, that goes to 0. Plus, that's 12x minus 6x squared. Okay, that would be 12x. That would be 6x squared with the minus sign. So let's factor and solve this and create a little number line. This is the way I like to do things. I'm assuming it's the way you do things here too. But if I take a 6x and factor that out, I have 2 minus x. All right? Set that equal to 0 because I want the critical points. I want to figure out where the first derivative is 0. That happens when x is 0 here and when x is 2. And then I put it on a number line. Okay, actually, should I create one number line for the first? I'm getting ahead of myself. All right, so let's do this. Let's stick with this. At 0 and at 2, this is my x value. My first derivative is going to be 0. So let's pick a number in between, 1. If I put a 1 into this first derivative, I'm going to get a positive value. I'm going to 12 minus 6, which is positive 6. Let's put in a 3. Right, if I put a 3 into this first derivative, I will get a negative value. I'll get 36 minus 54. So it'll be negative. I don't care what the exact number is, 18, negative 18, but I just care about the sign. Let's pick negative 1. Okay? If I put negative 1 there, I got negative 12 minus a positive 6. It's still negative. Okay? So the only interval where my first derivative is increasing or positive is between 0 and 2. Right there. There's my positive. I need to do the same thing for my second derivative. So let's go back. The second derivative, which is the derivative of the first derivative, is 12 minus 12x. Okay, and that equals 0 at only one spot when x is 1. Okay, so I'm going to go here. When x is 1, my second derivative is 0. Okay, let's pick some easy numbers. Let's put a 0 in and see. If I put a 0 in here, I get 12 minus 0. That's positive. Okay. If I put in a 2, that's 12 minus 12 times 2. It's 12 minus 24, which is negative 12. Boom. There you go. So my second derivative is positive here. That's when my second derivative is positive. So that's when it's concave up. All right, so I'm going to put both of these on the same number line. This is what I like to do. Here's my number line. Okay, here's my first derivative, my second derivative. I put them on the same, and here's x. I put them on the same number line on top of each other. And I get the critical points at 0 and at 2. This is for my first derivative, right? It's negative, 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 negative. It's 0. And then it's positive, 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 0, negative, 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 negative. Now let's do the inflection point where my second derivative is 0 at 1. Now I'm going to do above that. This is my second derivative up here. It's positive all on this side. And it's negative all on this side. Now, where are they both positive? They are both positive. Right here. See where the plus signs are on top of the plus signs? Between 0 and 1, which means choice A. All right? I just like the visuals. They're good stuff. All right, 17. A particle moves along the x-axis so that at time t equals 0, its position is given by x of t, which is 12e to the negative t sine t. What is the first time t at which the velocity of the particle is 0? Velocity is derivative of position, so the derivative is 0. Product rule, first times derivative of the second plus the second times the derivative of the first. So let's do this. Go here, go here. First, 12e to the negative t. Okay, times the derivative of the second. The derivative of sine is cosine of t. Plus the second, which is sine of t, times the derivative of the first. The derivative of 12e to the negative t is 12e to the negative t times the derivative of the exponent, which is negative 1. Negative, okay? Negative 12e to the negative t. All right, so this is what I want to do here. I am going to factor out a 12e to the 12e to the negative t. I'm saying 12e negative t a lot. So I've got this I'm factoring out and this. The negative sign here is going to stay behind. I'm just taking out the 12. So I've got 12e to the negative t times cosine of t minus, okay, because that minus sign got left behind, minus sine of t. Okay, so I need to figure out where this equals 0. This value will always be positive, so it's really unimportant. But if you want to say to yourself, well, you know, how would I get rid of it? I'm going to divide, I can divide both sides by 12e to the negative t. And if I divide 0 by 12e to the negative t, okay, this goes bye-bye, and this goes bye-bye, and this goes bye-bye, and whatever. So this will have no effect on it anyways. So I really need to see, in order for cosine of t minus sine of t to be 0, they have to be the same value, right? If this was 5, I would have to take away 5, okay? Or you may say to yourself, well, Visca, how do I do that algebraically? I don't know. Let's just add sine of t to both sides. Add sine of t. So now my cosine of t has to equal sine of t, all right? And that happens at one place and one place only, 45 degrees. How do I know that? Because I know my special right triangles. Okay, 45, 45. 1, 1, radical 2. The sine of 45 is the same thing as the cosine of 45, okay? So my t should be 45 degrees. Here is the problem. It's not in degrees, okay? I know 90 is pi over 2. So if I want 45, I need half of 90. So why don't I multiply pi over 2 by a half? I get pi over 4. 45 degrees. Done. 18. Let f be the function given by f of x equals the integral from 3 to x of tan 5t secant 5t minus 1. Which of the following is an expression for the derivative of capital F of x? If I have an equation, yep, I should probably get my marker going. If I have this equation f of x, and it equals the integral from 3 to x of tan 5t secant 5t minus 1 dt. And I want to take the derivative, right? I need to take the derivative of this, which means I got to take the derivative of this. The derivative and integral are like opposites. They just cancel. And all I'm going to do is I'm going to put an x in where my t's were. Okay, this goes by with a derivative. That's part of the integral. It's the dummy variable. Okay, so the answer is tan 5x secant 5x minus 1. Boop. D. Simple. Okay, 19. Little bit of algebra work here, so let's get going. Let f be the function given by f of x equals 2 cosine x plus 1. What is the approximation for f of 1.5? Found by using the line tangent to the graph of f at x equals pi over 2. I need to find the line of the tangent. Y minus y1 equals m times x minus x1. And when I have that, I need to find the y value when x is 1.5. Okay? Here's the deal. I need to find, in order to get my line tangent, I need an x, which I have. I need a y, which I don't have, but I get that by throwing an x into the original equation. Okay, so this x is going to pop in here to give me my y. And then I need to find the slope, which is the derivative of the original equation at this x point. That will give me my equation of the line. Once I have that, I got to plug in 1.5 for x to find the y. All right. Now that is explained, let's do work. Okay, so y equals 2 cosine of my x, which is pi over 2 plus 1. Okay, if my x is pi over 2, I'm just going to plug that right in. I'm finding the y right now. Okay, the cosine of 90 is 0. Okay, the cosine of 90 is 0. Remember what the graph of cosine looks like? Look at that. Here's 180, here's 360, here's 270, here's 90. Right here, I'm at 0. So this is like 2 times 0 plus 1, which equals 1. 1. All right, it's not bad. We're doing good. Now I need to find the derivative. Okay? F prime of x equals, all right, 2. The derivative of cosine is negative sine. So I'm going to say negative sine of x. And then the derivative of my 1 goes bye-bye. That's my answer. Negative 2 sine of x. I want this at the x value, pi over 2. All right? So we got to plug in our pi over 2 and solve. I've got negative 2 sine of pi over 2. That's 90, okay? Let's recall what sine looks like. Here's 90, 180, 270, 360. Sine is your S. Boom, 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 boom. So right here, I'm at 1. So we have negative 2 times 1, which is negative 2. That's my slope. All right? These are all just recollections of what you should know coming into here. If you don't know what sine and cosine look like, you best know before the test. All right, so it's negative 2. All right, so if I need to find y, they're asking me, what's the y value when x is 1.5? So I need to throw 1.5 in here and solve for the y. All right, so now let's make this easy. Let's add 1 to both sides. Let's solve for our y right now. So y equals negative 2 times x. They're asking me to use this line to approximate when x is 1.5. minus pi over 2 plus 1. And that's what my y equals. All right, there we go. I'm going to have to distribute this. Okay, negative 2 times 1.5 is negative 3. Negative 2 times a negative pi over 2 is just going to be positive pi. And then we still have our plus 1 on the outside. Okay, so we just did this. And negative 3 plus 1 is negative 2 plus pi, which if they want to write it, you can put the positive pi first, then the negative 2. All right, that was a lot of work. So the answer is C. Woo! That was a good one. Healthy. Healthy for the brain. Number 20. And the last one for today's video. Let f be the function given by f of x equals x minus 2 over 2 times the absolute value of x minus 2. Which of the following is true? Okay, you can say there's an asymptote somewhere at x equals 2, but that's not true. Keep in mind, you don't have a graphing calculator for this. You can't just graph this and look at it. Now, vertical asymptotes, how do you find them? It's whatever value of x makes the fraction undefined. And you might say, well, if I put a 2 in here, I have a 0 in the bottom, and that makes it undefined. Be careful. Vertical asymptotes do happen at values where x's are undefined. But if you can cancel something out, you see how this x minus 2 can cancel with this x minus 2? Okay. If you can cancel something out, you end up with this, okay? Because there's a 1 still left up here. Whatever is gone, okay, x minus 2, whatever used to be in the denominator that would have made it undefined that is now gone is not a vertical asymptote, it is a whole, okay? So think about it this way. If I have a line, okay, and I fill this in, this is my coordinate right here, all right? There would be a vertical asymptote with x minus 2 in the bottom. But if I remove this, where would have been a vertical asymptote is removed, and it's a whole. Okay, that's the easiest way to remember it. If you cancel out something from the bottom that would have made it undefined, you take it out. You take it out, so you take out that point, and it becomes a whole. So a whole is a removable discontinuity. What you need to determine is there a hole and the line keeps on going? Or is there a jump? All right, well, let's see what happens. All right, let me erase some of this right here. And at this point, I just plug in some numbers and figure it out. I'm going to plug in the number 1 and 3. All right, so if I have a table, and here's 1, 2, 3. Here's where there's going to be at least some sort of hole or undefined thing here. But what's going to happen at 1 and 3? If I put in a 1, 1 minus 2 is negative 1, and so I would have a negative 1 up here, and 1, okay, minus, what do we got? It's a negative 1, but it's the absolute value, so that's positive 1 times 2. I end up with negative 1/2, okay? If I put in 3, I have a positive 1 in the top, and then I still have a positive 2 in the bottom. It's positive 1/2. So there is a jump. Boom. That jumps. If I graph this, okay, remember, we said if I take these out, I end up with 1/2. The absolute value bar tells me sometimes it's positive, sometimes it's negative, okay? So I end up with, let's say here is x equals 2, okay, 3, 1, 1, 3. All right, my y value here is going to be negative 1/2, My y value at 3 is going to be positive a half. It's going to look something like this. Okay, and it is definitely going to be a jump. Woo! Strange, peculiar, but good to go. We are done. Problems 1 through 20? 20? Yeah, 1 through 20. I lied. It's 11 through 20. We're all done. Give the video a like. Follow me. I'll put more stuff up, and I hope to see you soon. Best of luck in that math class. Go get 'em, Tiger.